Hello student, in today's lecture we will learn something called moment generating function. Moment generating function. Okay, so I will define obviously what do you mean by generating function, and we already learned what about moments. So we'll talk about raw moments, obviously. This is already learned in the class, raw moments of random variables and central moments. Central moments. This is already done in the class. So let me first define what is a moment generating function, and then we will learn why this name. So okay, so the moment generating function, so let x be a random variable. Okay, so it can be either discrete or continuous. So we'll come. So we define the moment generating function. Moment generating function of x is defined by so we define this by x stand for the random variable and the real variable t. So this is defined by expectation of e power t of the random variable x. Okay, so t is real number. Okay, so obviously we know these values. When x is a discrete random variable, then it is nothing but sum over x e power t. Small x is the value which is taken by the random variable x, and then probability mass function. Okay, so it's for this is discrete space when x is a discrete random variable, and for continuous case this is minus infinity to plus infinity e power tx into probability density function. Okay, this is for continuous case. Clear? So by definition we define moment generating function is the expectation of this new random variable exponents of tx. Okay, so now let me let me discuss why it is called moment generating function. So this term generating function is a term from combinatorics. Generally people use in combinatorics. Okay, so what is that? So suppose you have a sequence, some sequence of numbers, say an. Okay, so let me maybe assume that n is say natural number or maybe whole number. Okay, so natural number union 0. Okay, and we would like to know that does there any function which generates this sequence of numbers n, and then we define the generating function by this quantity. This is summation over n x power n. Okay, so this is called, this is one type of generating function. This is called binomial generating function. Okay, and there is one more type called exponential. So this is the binomial generating function. Binomial generating function. and then you have there are many types of, okay. So we have let me just tell these two things. um, Something called exponential generating function. So what is that? So this is a n x power n y factorial n, okay, and then n equal to 0 to infinity, okay. So this is are called exponential expo okay. So exponential generating function, okay. And our moment generating function is one type of generating function which is actually this kind of exponential generating function. And here for moment generating function, it is actually these n's are nothing but our raw moments. So the nth moments is a nth raw moment of the variable x, okay. Clear. So what does that mean? That means the moment generating function actually generate the raw moment. So let me just tell one more thing in detail, so then you will have more better understanding. So you can write down this exponent of e power tx. So let me assume that is very good condition, and all the nice function, all the properties are true. So we can write down this 1 plus tx plus tx whole square by, I'm assuming that I can expand by these, and then you can use this linear property to write down this is t time expectation of x plus t square by 2 factorial in expectation of x square, and so on. Now you can understand that this is one type of exponential generating function, okay. And if you look at this, expectation of x is the coefficient of t. Similarly, expectation of x square is coefficient of t square by factorial 2. This is factorial 2. So let me write down properly 2 factorial, okay. uh, and then this clear that this function actually generates the moments. So moments are actually sitting as a coefficients of this t square t cube by obviously n square, okay. Clearly. So now let's have some more examples. So you start with what is, say, mx when t equal to 0, then what happens, then it is expectation of e power 0x, which is 1, okay. And what is clear. Now how do we get this the first moment expectation of x, so that you can easily get. So this, so if you take derivative with respect to t, ddt of mx t, and then you evaluate at t equal to 0. Here you evaluate at t equal to 0 for the first one already. Now here t equal to 0, what happened, what you get? So you'll have um, ddt of expectation of e power dx, okay, with respect to t equal to 0, okay. And then you know that expectation and derivative, we can actually so I'm assuming that the functions are nice. So whatever we learn in the class, whatever distribution for which you can obviously can do these changes, expectation of interchange of derivative expectations, okay. So So I'm assuming these formal things, and then at t equal to 0. Okay, and so yeah, so sorry, so this is this, and then we can find out that this is nothing. Okay, so then you can find out that uh, ddt of mx t at t equal to 0 is nothing but expectation of so yeah, so what was that? So e power tx, and then you have x time that, so it will be nothing but expectation of x time e power tx. Okay, and then you evaluate at t equal to 0, and when you evaluate t equal to 0, you will have expectation of x. Okay, so what does that mean? That mean and it is clear from this series that expectation of x is nothing but the coefficient of t. So you can find out, so if you have this kind of Lorentz series function, then you can find out easily expression of this. Similarly, so similarly as this your second raw moment, you can find out as this double derivative, or I can obviously at t equal to 0, or you can write down, so, and in general in the nth moment, nth raw moment, you can write down as, okay, so let me write down, so this is actually m dash x0. Okay, and then this is m double dash x0. Okay, and then you can, in general, you can write down that m n a derivative, and then at 0 it equal to 0. Okay, so so what does that mean? That means this function actually generates all the raw moments. So this is why we call it moment generating function. Okay, now give us let us discuss some examples. So start with examples. So example number 1. So we learn something called binomial random variable. So let us discuss about binomial random variables. Okay, so we have x, which is say binomial with parameter n and p, and then how to get the moment generating function. So obviously we will use the definition. So this will be nothing but expectation of e power tx, but we already know this is nothing but summation e power, so let x a random variable taking value k, so it is k, and k equal to 0 to n, it takes values from 0 to n, and then the probability mass function. So what is the probability mass function? So probability mass function, so let me write down here k. Okay, and mass function is of this form: k equal to 0 to n e power minus tk, sorry, e power tk into n choose k into p power k 1 minus p power n minus k. Clear? So I just use the probability mass function of binomial random variable with parameter n and p, and now we need to just manipulate. See, this term and this term we can take together, and then you can write it down as summation k equal to 0 to n, and then n choose k, and you see e power t and p whole to the power k, and then 1 minus p to the power n minus k. Okay, now look at this thing. This finite sum is actually a binomial sum, and then and the value of the sum is p into e power t plus 1 minus p to the power n. Clear? So this is our result. So this is our the moment generating function for Barnum random variable, right? Now you can check it. Why, how, whether this function actually gives you all the moments or not. So how do you check it? So we need to check that the mean, the expected values, maybe, and then the second moment, variance, everything you can check. So let me check it for what about mx dash t. So I mean dash mean dt. Okay, so if you do the derivative dt of these things, so p power t plus 1 minus p to the power n, right? So now if you take derivative, so you'll have p times e power t plus 1 minus p to the power n minus 1, and the derivative of this thing, which is, if you take derivative of these things, obviously n into, obviously n will come first, n into this, and then derivative of inner things, so this is nothing but p into e power t. Okay, so these are 1 minus p is constant. So this is that derivative with respect to t, and hence if you can find, if you want to find out m dash t equal to 0, which is the expectation we already know, and then this will be nothing but at t equal to 0, this vanishes, so this is p, so this vanishes, so np. And now you can recall that is exactly the expected values of the value of the binomial random variable with parameter np. Okay, and now you can easily find out second raw moment. So for second raw moment you need to just take double derivative, and what will be double derivative? Double derivative will be so let me do it for you. So n into n minus 1, and then p times e power t plus 1 minus p to the power n minus 2, and then you have p et whole square. Okay, this is effective derivative of the first term, and the second, there will be another second term, which is you need to take derivative with respect to pt. So for that you will have n times, so this is constant first term, 1 plus 1 minus p to the power n minus 1, and then p into e power t. Okay, so this is this derivative at t equal to 0. This is the value. Okay, so the second raw moment, take double derivative, and then you evaluate at t equal to 0. So if you evaluate t equal to 0, you see this term is 1, and then this is p square, so you'll have n into n minus 1 into p square, and here when t equal to 0, so you'll have p here, and then np, so this is np times this. Okay, so that second raw moment is this, and hence you can find out the variance, which is the second central moment, which is nothing but expectation of x square minus expectation of x whole square, and then n into n minus 1 into p square plus np. Okay, and then n square p square. Now you see that in first term n square p square get cancelled, and you will have exactly np 1 minus p. And now we recall that is exactly we learn the variance of binomial random variables. Okay, clear? So okay, so far so good. Now let us try to do it for another discrete random variable, say Poisson random variable. Now for Poisson random variable, so you have Poisson with parameter say lambda. Okay, and then we can easily find out that mxt is nothing but expression of e power tx. Okay, and so suppose again taking value 0 to infinity, and then e power tk and e power minus lambda and lambda power k by factorial k. Okay, and now so e power minus t is independent of k, comes outside, and then the sum you can write down as e power t into lambda whole power k by factorial k. Now we see that this is again a exponential sum, and the value, the sum is what? Sum is e power lambda e power t, and then finally you will have e power lambda times e power t minus 1. So this is the answer. Okay, and again now homework, you find out that exactly in this case also you can find out m dash 0, which will be expectation of x. Okay, and then you find out that it is for t equal to 0, it is actually lambda, and similarly m double dash x 0, which is the, this is a homework you find out, and the variance you already know is also lambda. Okay, you find out, you can always find out from the problem. Okay, so now coming to that continuous case. For continuous number variable, can we do it? The answer is yeah, we can also do it. So so let us start with this uh, example, exponential random variable, which you already learned in the class. So exponential random variable. So we have exponential. Suppose now you remember that the PDF of exponential random variable with parameter lambda was of this form, right? 0 whenever x is greater than equal to 0, and I already assumed that lambda equal to 0, otherwise 0. Okay, so how to find out the homogeneous function in this case? So in this case it is minus infinity to the plus infinity, but obviously for 0 to minus infinity it is 0, so I will come back to that. So e power tx e power minus lambda x into lambda and then dx. Okay, so then this is write down as lambda times 0 to infinity, because from 0 to minus infinity to 0 the PDF becomes 0, so the support of the function is on 0 to infinity, and then we will have e power t minus lambda x dx, right? Now we need to do this integral. Now you check that this integral may not converge always. Okay, now under what cases this integral converge, that we already discussed in the class. So if it is kind of a decreasing function, and then you can talk about the convergence of these integrals, and you see that that is true whenever t minus lambda is negative. What does that mean? That means whenever t is less than lambda, if t is less than lambda, in that case the function is, this integral is converging, and then what will be the value? So you can easily find out that when t less than lambda, this integral is nothing but this will be nothing but lambda minus t. Okay, this is for t. So so what does that mean? That means for exponential random variable, the moment generating function does not exist always, so it exists only for t less than lambda. Okay, so this is an example that sometimes it is may exist or may not exist. Okay, and again if you want to find out your expectation everything, so you can do it derivative. So this is what, this is ddt of lambda over lambda minus t, and then at t equal to 0. Okay, and then this will be nothing but lambda over lambda minus t whole square at t equal to 0. Now t equal to 0, so this gives you 1 by lambda. If you equal it, and this is the mean of the exponential random variables. Now homework, you find out the other moments variance. So find out what is the second raw moments variance of exponential random variables. Okay, now one more important random variable, very important, we learn, that is called normal random variable. Okay, so this is I need to discuss in detail. So normal random variables. Okay, so we'll start about with that standard normal. So suppose Z is a standard normal, so that means Z is now distributed with parameters 0 and 1. So 0 is the mean and 1 is the variance. And then how to find out, and then we will do it for the general case. So for this case, what happened? For this case, we know that we can easily use definition. So this is expectation of e power t z, and so this, suppose z is taking value x, so it will have minus infinity plus infinity power dx, and then for standard normal distribution, the PDF we know dx, and then 1 by 2 pi, right? Yeah, so this is we already know from our previous classes, and then you can write down that as minus infinity to plus infinity e power minus x square minus 2x t by 2 dx. Clear? Okay, so now we will do some kind of calculation here. So let me do it. So this you can write down e power, the numerator you can write down x minus t whole square. So we just add it and subtract, and then minus minus plus, so it becomes here plus t square by 2 dx. Clear? Okay, so now you check that. So this inner integrand is okay. So let me write it properly. 2 pi minus infinity plus infinity, you can write down as e power minus x minus t whole square by 2 into e power minus t square by 2 dx. So this part is independent of x, so you can take outside. So it is 1 by 2 pi into e power minus t square by 2, and this famous integral, and that we already discussed several times in the class, and we know how to calculate it. Okay, there are many ways you can calculate it. One of the ways is using gamma function, okay, that we have done in the class. And yeah, I think there is sorry, so I think this is minus, this minus, this you take plus and minus, so minus minus plus here. Okay, so this should be plus here, this is also plus here. Okay, so e power t square by 2, and then this integral. Okay, so now this integral we already discussed in the class, and we know that the value is actually 1 by root 2 pi. We already has done several times. This is sorry root 2 pi value, and then this get cancelled. The final answer is e power t square by 2. So this is the moment generating function for standard normal random variables. Okay, now what about for general case when x is normal distribution with mean mu and variance sigma square? Okay, then we can write down x is in terms of mu plus sigma z, and we know that you can convert from any normal distribution to the standard normal distribution, and this is the formula. Okay, and we use our property on this formula. So sorry, we use our formula. So mx of t is nothing but e power exponent of e power tx. Okay, so now this is we can write down as exponent of e power x is nothing but mu plus sigma z. Okay, sigma z, capital Z. Okay, and that you can write down as expectation of e power t mu into expectation of t sigma z. Clear? Now e power t mu is a constant because this is with respect to the random variable z, and then you can write down as e power t mu of expectation of e power t sigma z. Okay, now we check that what is this expectation. So this expectation is nothing but moment generating function of z at the point t sigma. Clear? And we already know the moment generating function of z, which is this one, and then we will use this result, and hence the moment generating function of t will be of the form. So we have e power t mu. So first write down e power t mu, and then mz of t sigma, which is nothing but e power t square sigma square. Okay, by 2. Okay, and then you write down it is in terms of e power sigma square t square by 2 plus t mu, and this is the answer. So this is the moment generating function for a normal random variable with mean mu and variance sigma square. Okay, now we can easily find out from these results that first raw moment, which is the expectation, and the second raw moment, and then with that help we can find out that variance. Okay, now check it. These are homework, you can easily check it at home. Now we will try to discuss some properties. So the most important, why it is very important. So moment generating function is actually uniquely, so let me write down this is unique. So what does that mean? So the moment generating function uniquely determine the distribution. Okay, so what does that mean? That means suppose you have a homogeneous function, you know a function, and then you check it is known and you check whether it is matching with some of the known thing or not. And if it is matching with say binomial thing, then this x must be a binomial random variable. And you also can see that for every random variables the homogeneous function is unique. Okay, so this is very important property. By this property we will check that sometimes if you want to check whether some random variables is binomial or exponential or something, it is easy to find out the moment generating function, and if it is matching with that parameters, then you can easily tell that this is the binomial or this is the exponential or this is a normal distribution. Okay, and one another property. So what happens? Suppose you have two random variables x and y. Okay, and they are say independent. Then what about their sum? So what about their sum? Like, can you find out the moment generating function for the sum? The answer is yes. So you can easily find out. So you can write down it is expectation of t time e power t time x plus y. Okay, and then we know that this you can write down as expectation of e power tx into e power ty. Okay, and we already learned this thing in one of my this online lecture series that whenever x and y is independent, and then any function involving gx and gy, they are product of the expectation is nothing but the they are if you take the expectation of the product, it will be the product of the individual expectation. So it is nothing but expectation of e power tx. So this is I am using the independentness here. Okay, and expectation of e power ty. Okay, and we already know this is nothing but moment generating function of x, and this is moment generating function of y. So what does that mean? That means if we have two independent random variables, their sum will be if you want to find out the moment generating function of their sum, it will be the product of the individual moment generating functions. And you can also extend these 2 by 3 4 also. So obviously if they are independent, you can do it. Okay, so now easily, so as a result you can easily find out so for example sum of two binomial random variables. Okay, then how to find out? So let me give an example. So suppose you have this is binomial say n1p and binomial n2p, and then you know that m x of t is nothing but remember p into e power t plus 1 minus p to the power n1. Okay, and for this will be p into e power t plus 1 minus p to the power n2. So if you want to find out what is this x plus y, and suppose that given that x and y they are independent, then you can find out that this is so in sum of two independent binomial random variables, this is again of the form p e power t plus 1 minus p to the power n1 plus n2. So what does that mean? That means if you take sum of two binomial random variables which are independent, then their moment generating function is this, which is again satisfying the binomial properties. So x plus y is a binomial with parameter n1 plus n2 and p. So this probably tells you that looking at moment generating function, you can determine that distribution also, right? Now you can do this homework. What about some of also some of normal other things? And you tell me. Okay, so for example, normal is also important. So let me give for normal. Suppose we have normal. So this is mu 1 sigma 1 square, and then uh, mu 2 sigma 2 square, and the independent and then let us find out whether the sum is normal or not, and you can easily find out for moment generating function, and you see that this will be. So what was that? So for first one, it was e power uh, mu 1 t plus sigma 1 square t square by 2. Okay, and then for the second one, it is mu 2 t plus sigma 2 square t square by 2, and then you can write down this as e power sigma 1 square plus sigma 2 square by 2 into t square, okay, plus mu 1 mu 2 into t. And now it is clear that the sum of two independent normal random variables is again a normal random variables, and this is that mean of that this is the variance. Okay, so this is the mean. This is the mean x and y. Okay, not x and y too. So x and y, and this is that variance. Okay. Okay. So I mean there are. I mean you can obviously find out many such functions. So now let me ask a simple question. Similarly, whatever we discussed in the last two classes, in fact, yesterday's lecture we discussed. So we can do here also moment generating function, moment gen function of the sum of random number of random variables and number of random variables. So remember we have done for expectation and variance and variables. So what are the assumption? Assumption is that you have x1, x2, x2 and so on. They are IITs. So what does that mean? Independent identical distributed random variables, and you have another non-negative random variables. Let me assume that be a non-negative so let me say integer valued you take value only integer. This is going to help me. Random variable which also independent with this each xi. Okay, And then we want to know what about the sum of, so if you define y is summation xi and I is from 1 to n, so this is the random number, sum of random number of random variables, so capital N is varying. Okay, then can you find out how this boundary function look like, and with that help of we can you see the distribution things. So obviously you can do it. So let me first find out what about the conditional expectation. Uh, so okay, so this conditional expectation of y given n equal to n, what is this? So let me find out first then. So this is rather sorry, e power, you could say e power ty. So okay, so I need to find out my of t, which is expectation of e power ty, which is expectation of e power t summation xi I equal to 1 to capital N, which is also random variable. Okay, so so we will try to find out this thing. We have to find out that condition, because we know that this is nothing but expectation of e power t summation xi equal to 1 to n, and then um, e power, so yeah, so and then with respect to say n, yeah, so this is the property expectation of x given y, it's nothing but this. Okay, so we will try to find out this inner part first. So let us find out. Now to find out the inner part, what we need to find out, we need to find out what is expectation of e power t into summation xi I equal to 1 to capital N, and when n equal to small n, when n takes value small n. So in this case, what happened? In this case, we know that the sum will be till up to small n, so you can write down e power t summation I equal to 1 to small n xi and n equal to n. Okay, and then this is n and x are independent, so I can write down that expectation of e power. So now I am using the independentness of n and xi. Okay, so e power t summation xi I equal to 1 to n, and then you can just interchange that, and also you know that you can write down these x's are independent, so you can write down as expectation of e power t x1 and e power t xn. Okay, and then this independentness gives you this, is nothing but product. So now already also you know that x's are IID, so they have the same homogeneous function. So you have m x t to the power n, where m x t is nothing but the moment generating function of each mi, m xi. Okay, they are IIDs, they are the same homogeneous function. Okay, clear? So this is for true for every n. So if this is true for every n, then what happened? Then you can write down what is expectation of then e power y dy n, and then this is mxt the whole power n, and hence moment change function of y of t is nothing but expectation of or ty given n, which is nothing but expectation of mx t to the power n. Okay, so this is the answer. Now if you have random variables which are random number of random variables, if you want to take sums, then you can do it by this. Clear? Okay, so this today we'll stop here with our discussion, and now I am going to ask you this uh, quiz 3 question. Okay, and I expect you, today is 2nd of April, so I expect you to submit this by 3rd April, as your class representative told me that you need more time, so I am giving you time till 3rd April, say mm, mm, okay, how much time you need? So not today, not till midnight, today midnight, so maybe 3rd April midnight. Okay, so let me give you more time here. So I'm giving you almost 32 hours, 30, more than 30 hours. Okay, but no problem. Okay, so I think now you can solve the problem and send it to me. And note that I have already find out some people are copying actually, because they are doing a similar kind of mistakes and other things. Okay, so obviously you can understand that, and if you do this kind of practice, it is going to those who are copying, they are going to be they themselves are punishing themselves, because in the exam when you will have question, you don't know how to find out. Okay, how to solve this problem. So so let me find out a suitable problems for which you can find out you can find out yeah, so maybe this is interesting. You can find out something called this problem. So it's called conditional covariance formula. Okay, so suppose you have x, y, and z, three random variables, and you know their covariances. Uh, so let me define it. So we define covariance of x, comma y given z is nothing but expectation of x minus expectation of x given z, okay, into this into part is here y minus expectation of y given z, and the whole thing with respect to given z. Okay, so this is the condition covariance of xy. So this is called covariance of xy given z. Okay, so this is called conditional covariance of xy given z is another random variable. Okay, so that is given by, so you remember for covariance you have x minus x into y minus expectation of y, right? So instead of that you have expectation of x given z, expectation of y given z, and whole thing given z, right? So this is formula. Now with that formula you find out this. So you find out number one, um, covariance of, obviously is a simplification. You need to do simple problem x with z, you can write down as expectation of xy with respect to z, and this is same as unconditional one. Okay, and number two is the covariance formula. So that conditional covariance formula. So this was conditional covariance. Now the main formula, the covariance, you can write down as covariance of xy, you can write down as expectation of covariance of xy given z plus covariance of expectation of xz comma expectation of yz, and this is expected. Okay, so this, you remember we already proved the conditional variance formula. Okay, so you can find out these, and then number three, verify conditional variance formula, which we already discussed yesterday's lecture, last lecture. Variance formula from formula 2. Okay, clear? So if you remember in last talks we already discussed conditional variance formula, and that is a special case of conditional covariance formula. So you do the conditional covariance formula and find out this 1 and 2, and then check that 1, 2 and 3. Check that the conditional variance formula is a special case of conditional covariance formula. Okay, so by this we will finish today's lectures, and I have given you more time this time. So all the best, and submit the solution in time. Okay, bye.